Should we wait or get started? Get started? Okay. All right, so today I'm going to be talking about the sim-to-real gap and how people are thinking of bridging that gap. So I think a few people asked questions about this last week, and for anyone who's thinking about going into hard robotics, taking their code out of sim and putting it on a real robot, these are problems you're going to encounter. And I think it's good context, or it's good to have context about approaches that people are using either during the training phase or during the deployment phase or during the iterative stage. I will also apologize in advance if I like randomly start hacking out with a cough, but hopefully it'll be okay. All right, so when we think of like success in a simulation, that's great. It's a great first step, especially when you're working out the theory. But in the case of robotics, that's just a start. Most of the times you take something out of a sim and you go apply it in the real world. They're like, it's very rare that you would get a completely successful run immediately. And people have broken it down into a few different types of gaps. So for those of us working with perception and vision, when I say a visual gap, that's not just with cameras, that's with LiDAR, any sensors really. How you perceive the environment will change in simulation versus real life. I mean, when you think about it, even for us, like in simulation, for example, if you only trained with sunny data in a simulation, even if you trained with sun like data during the day and during the night, if you think about it for us, like on a snowy day, on a really snowy day versus a less snowy day versus no snow at all, the conditions look very different, right? We perceive the world differently. Another thing to think about is even us as humans, we like you and I will look at things very differently. So there was that whole debate of what color is the dress, right? Like blue and black or white and gold. Each person's perception of things changes based on the conditions that are around them. And if our simulators don't have that type of don't simulate that, then we have no way of making sure that the robots encounter situations like this and then learn how to do it. So for these systems, like especially imitation learning systems where the robots learn what they're dealing with, right? Like they encounter a certain type of situation and they learn how to. And even then, like there's no guarantee that like just because you've trained like say out like the campus in a simulation and I train. Right, so visual gap, dynamics gap is usually where something like that comes into play. So simulations, especially for them to be fast enough for us to do training, like parallel training or multiple iterations at the same time, we're gonna have to simplify a lot of the characteristics that are Russian or gravity is pretty easy to simulate, but other type of vehicle dynamic, you can't really measure if a robot, like if a motor is old, it might run for a little bit and then it might have issues in certain parts. There's no way for us to solve that issue. Right? So, and then the third is latency, which becomes important or when you're dealing with things that need to happen at a quick clip or quick. Perfect. So but in the real world, if you have your policy coming out at 100 hertz and then you like your LiDAR 1,000 like 1 kilohertz, if even one is off by a little bit, you might be using old data on a new policy output or whatever it might be. And when your simulations or your robot execution relies on things being exactly like they are in sim, then something like that can really screw you up. So this is meant to be like a during training in sim, a chef, you can think of like a chef who's learning how to use like plastic ingredients. Things don't go bad, the colors are pretty similar, blah, 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 whatever. But then when you're dealing with real ingredients, you have to worry about like, oh, maybe my peppers have gone bad. How do you tell, right? Like in simulation, you can't really tell because you were given something, you were like given the best version of it, and then now you're getting a slightly better version of it. So these are problems that we have seen in our lab, these ones. And something even as simple as like in simulation, you test on a carpet, but in the real world, like carpets are very different, right? You can have a really low carpet or you could have a very like, tall rug. So we had a situation where we were changing surfaces. We were exiting like the lab floor, which is similar to this, entering the main hallway, which has like a really thin carpet, and then going into our lab space, which has a nice fluffier carpet. And like it tried to get over it was fine from this surface to the low carpet because I guess that was relatively well simulated in simulation. But the higher carpet was a real struggle for the robot. And barring that, it would have executed completely fine, right? Like the plotted trajectory looked right. It just like encountered situations in the real world which messed with it. Similarly, like things like battery power are not things that simulate, like you just assume you have infinite battery for the most part in sim. And battery power, especially with drones, is a huge issue. Especially like if you're carrying payloads, or so for example, for the VLN team, if you wanted to take out, if you wanted to actually execute the paths that you're generating, you'll probably find that the path you've prescribed is not going to be followed exactly, or you'll have some issues with the actual execution once deployed. And the reason, again, are typically we use much simpler physics models, so it's easy to generate multiple trajectories and train them simultaneously. Also, we tend to use Gaussian models to represent noise in sensors, but that's not always accurate. So people have found that for certain types of sensors, there are better models that you can use other than just Gaussian noise. But you either have to tune them or you have to, like, there's an extra step involved. So tuning that in your simulator really depends on how much you care about the fidelity of that sensor and how different the real world is from what you're encountering in sim. So for example, in my case, the sensor data is a core part of how it works. But because we do like a filtering process and we're only taking these sensor signatures and abstracting them away, it's okay if it differs between sim and real. I don't mind that much. But for some people, like they need very, very precise knowledge or like pretty good guarantees that their real sensors don't have that kind of noise. And so for them, that's a priority. So an important thing when you're thinking about bridging that gap is what is a limiting factor when you move it onto the robot, right? Like what is it that what could go wrong in the real world, which would mess up your execution of your policy or your whatever your system is. And then you need to kind of re-engineer that. So sim2Real is an engineering problem for the most part. You kind of just need to identify what it is that needs engineering. So this is a simple video. It's supposed to drive straight in sim, but if you look at the video, if it went straight, it would go here, but it's veering off the path, right? So it could be any number of things. It could be like the right motors are less powerful, so there's like a slight turn in the radius, right? Like there are any number of things that could have happened. Maybe both sides are controlled by different batteries and one battery is less powerful. Or maybe there's something on the road, right? Like the road structure is not flat, which was an assumption we had. So it's interesting to see that even for something as simple as driving in a straight line, which shouldn't be that hard, is quite hard. And you'll see that the only thing that's getting toggled is the forward and backward button. And the forward, backward, and left, right are isolated to show that it's not even like human error. So if it can't even do this, like in certain situations, if it can't even do this, then it makes sense that like as you get more and more complicated, there are any other number of things that come in and mess us up. So the examples over here are a lot, like some of the commonly used techniques in the field, and they appear at different points of time in execution. So for example, the first one happens during the training process. So this is something you guys might be more familiar with. It's the same way that you can like add adversarial data to your training data, or you can go in and modify it. So our original data is maybe captured at noon on a sunny day. And then you can go in and you can add fake snow, or you can add clouds, or you can like change the lighting, or you can skew the image. You can do any number of things and then retrain your model and see, is it able to still figure out what you want it to figure out, even with these distortions or these problems. And so in a similar way, you can do the same thing with the simulation dynamics. So you can go in and change the mass of the vehicle. You can go in and like reduce the battery level, or do that thing where one wheel is more powerful than the other, or like the motor for one wheel is more powerful than the other. And if you're able to like tune these parameters and then maybe train a policy that can still produce reasonable outputs under this type of distortion, then when you go execute it, you have a much higher likelihood that these issues won't actually affect you. Again, like you may fix for 5 out of the 10 possible problems, and that could solve a good bit of the common issues that you encounter. But domain randomization is not like a short shot way of removing all your problems when you bridge that gap, right? So typically people will test their policy right out of sim with maybe some safety barriers, and then see how that executes, see how that performs, and try to like re-engineer and try to figure out what went wrong and how can I fix my sim, or how can I fix my robot to then prevent that from being an issue. So item 2, SysID, or system identification, is pretty much that, where you use examples from, like maybe you drive the robot in the environment, and then you can pass that data in and then tune this simulator parameters. So you could take a generic simulator, and if it has parameters you can tune, you can figure out like, what is it that my robot needs? So the system identification is about the robot, not about the environment. And then that could, potentially allow you to simulate your specific robot in simulation to some extent. Maybe like 80% of your robot is, well represented. These next ones are kind of post exit. So once you've run something, you take a look at your results and you see what is it that needs to be improved. So these ones either have a continuous loop of sim to real to sim, or like the core testing is once you've executed a few iterations and you see how well it performs. So for example, here you use the sim for all your basic movement, meaning you still train a policy as we've been talking about. And then you have another model which can take care of basically that delta, which takes you from what your sim is producing for you in the real world to what you really need in the real world. And the whole point of this smaller model is then we don't need to worry about we don't need to worry about what is it that I need to model in the sim, right? This is just for my environment right now. This is the delta that I need covered. How do I learn that part? So you could take the same base model and apply it in different environments, and you'd need to retrain the smaller real world model based on like the robot that you're dealing with. So this is like, I have a generic policy that should work for most robots. Basically the high level like idea for these concepts. So just saying, yeah, what's up?
Sorry. I want to ask what kind of environment, a simulation environment data is being transferred to training, like other than visual?
So your robot might learn how to navigate in a simulation, right? And it might be used to certain types of road surfaces. So it has learned to output motor actions based on the type of not just based on vision, right? Like I'm using my vision to tell me maybe where to go. Vision could be part of the training. It could also not be part of the training. But if I learn that like on like if you think about it, if you drive too fast on a really smooth surface, you'll skid, right? You won't generate enough friction to keep yourself stable. So the robot might learn that on floors that look like this, where it's like really glossy, you should go a little slowly so you can maintain friction. But let's say we get onto wet grass, right? Wet grass is usually not a problem, but wet grass we would treat the same way as a slick surface. And what it should learn, or what it should know, is that when you encounter something wet or something smooth, you act a certain way, you go slower. But if it just tries to like run through it, it might just crash. So the point is like there are other components that like what is the model learning, right? If it's learning how to navigate or learning how to move and it encounters physical characteristics that it's not used to or it hasn't learned how to handle, then it'll lead to problems. That makes sense?
So wetness, it should identify based on visual.
It could identify that based on visual. It could identify that based on any other sensor. But the point is like if we haven't simulated wetness in the simulation, right? Or if like you and I know that the wetness is going to make it a slick surface, and then therefore we treat that slick surface however we treat any other smooth surface. But the robot hasn't encountered that to know that this is how we behave, right? So either you and I we can like make a model, we can add another module which says, okay, this is how you handle this type of terrain. This is how you handle this type of terrain. Like terrain X is like terrain A and terrain Y is like terrain B. And if the robot knows how to handle A and B, it should know how to handle X and Y. But unless we go in and make that, like add that layer in or make that connection for it, it's not going to know how to handle. So these are all like ways of like handling problems like that. So maybe not that exactly, but problems. Does that make sense?
Yeah.
Yeah, I think the key thing to remember is when we're talking about simulation, we're not just talking about simulated data. So that's one part of it. We're also talking about the environment that the robot is learning in. So like, it's great if there are good parallels between simulation and the real world, because then it's learned exactly what it needs to do. But if there's any sort of variation, then that's where the problems start to come. Okay. And then this last one is very interesting. It's a much newer space, I think. But the idea is like, can you capture examples of real world failures and then reconstruct like a digital twin type thing in simulation? So that's a lot more expensive of a process in that like
Is it being used now?
I've seen examples of it being used in certain types of outdoor navigation still. Especially when you connect it to map, huh?
That's impressive.
Yeah, yeah. I mean, very small cases. But I think, I mean, this is a very expensive process because to do that reconstruction in sim and then I mean, you're basically trying to take something in the real world and model it in simulation so that you can run your robot in there. But it's an interesting thought at the very least, whether it's usable. Okay, so these things are I kind of touched on them, but some of the important things to think about when you're dealing with hardware is like when a sim crashes, you just restart it. When a robot crashes, it's a lot of damage. So not only is it important that you test you have to test your policy in the real world, but you have to test your policy with e-stops or with conditions that allow you to like early stop or emergency stop or like extra safety barriers, basically. Like your collision avoidance has to be really good because you don't know what's going to happen once you deploy it. The second one is what I said before, but it's important to like test all the components of your system independently and see like what rate is my LiDAR coming at? Is it consistent? And the thing is when you work with like ROS systems, I'm assuming you guys are familiar with ROS, no?
But I've never.
Okay. So roboticists nowadays use ROS2, which is a newer version of the ROS system. ROS stands for Robot Operating System. So the way we have like iOS and Windows and things like that, it's just a consolidated way of like unifying how like robotics code is run and things like that. So
For ground-based robots or?
they have ROS for drones as well. So the idea of ROS is just you can have like Python or C++ or C code that feeds into these various nodes, and each node is like doing some type of operation. So you have a node which handles all the LiDAR data. You have a node which does vision. You have a node which runs your policy, like executes the policy. You have something for your motors. And the idea is like you have all these nodes, they communicate with each other. So in this case, when we talk about nodes, they are like graph nodes, but more importantly, they're communication nodes. So you can think about them as different people who are talking to each other and being like, I'm the LiDAR person, so I'm like, hey, I got this data, here you go. And then the next person's like, okay, let me take that and process it with the code that's within me that I've written. And then I will output something, right? So you can subscribe or you can publish across nodes. And the point is you can set those values, like what is your publishing frequency? How often do you want to subscribe to the sensor, to the LiDAR sensor, right? And handling those things is like great in theory, but then when you actually execute stuff, you have to make sure that everything's not going to be coming at a consistent like 300 hertz, right? Sometimes it'll be 306, sometimes it'll be 320. So there's some variation, and sometimes that doesn't matter unless you have a very, very frequent updater of some sort, which is relying on it. So mapping that out is super important when it comes to hardware. And then the last is again, like keeping your battery health, like battery health is super important for the robots and the execution. So like I run into issues where we like had 2 batteries on board for a different project, and then I just ran the robot, and there's just too much like like it wasn't a good model of the amount of power the robots were getting in sim. It would be like 1 battery equivalent. And then when the battery life starts to drop off like past 50%, the robot will like either move slower or like it'll just stop because like there's a limit to which, or it is used to handling, it's used to learning and training in an environment with 100% battery, which is obviously not realistic. You can't have the robot plugged in at all times. So keeping those things in mind becomes annoying, but like it's very important when you're actually testing your policy. That's why they say like, or I've been told like if you touch a robot during your PhD, it'll add at least a year to your PhD. And then if you work with humans, it'll add 2 years. And if you work with robots and humans, well, don't even think about graduating. So just because like you touch hardware, it'll break, and then you have to figure out the hardware, and then you have to figure out how your software works on it, and then your software will work on it, and then the battery will die, or something stupid will happen. And the number of times we've gone to like a field test and it like works perfectly, and then our PIs will walk by and then it'll just break and we're like, yeah, what's working? Okay, so here we have some more I would call them modern or like newer, yeah. Yeah. This one?
Be simulated having games.
Like some limited life.
And if you have
it's a good question. Like it's not hard to simulate at least some basic like linear reduction in your battery in a simulation. But a lot of the simulators we use just don't implement it because they care more about the like physics interactions and they're like keeping track of many other things on it. So there probably are simulators out there that do a better job of handling that. So say you added 4 passengers into a car and drove it around, it might have a good simulation of that. But the ones that we have been using don't really keep track of it at all, because there's this assumption that like to recharge, you'd have to go back to a base or do something, right? Like for us, it'll be like this ground robot that's just dropped into a field, right? You have no like charging station per se. I don't know why, like beyond the fact that it's another thing to keep track of, and typically simulators, like each simulator that's developed has a different purpose. You won't find one which is really good at everything, right? Because that'll be super expensive to run, and like, you know, I mean, different people have different priorities. So like you could see, like it's okay for us because we can run and then it can drop to 50% battery. We're following it. We just swap out the battery and then it goes back to 100%. So in our execution, we don't quite care how well that part is being simulated. We have our priorities are that the sensor data matches what we'd see in the environment, or that like we have diverse enough environments to test in, or we have that ability to model or like modify the environments. And this is just the one that was easiest to integrate in our spec. So that's why we don't use one simulator like that. But I would be surprised if there isn't anything that can simulate it. It just probably won't be as good at something else that might be important to you. So like a big part of, again, your training process and your testing process is looking for a simulator that meets whatever your needs might be. And typically that's like which simulator best models what it is that you care about in the environment. So like in my research, I care about the semantics, right? I care about the sensor data and interpreting that. So my priorities are going to be a simulation that gives me good high fidelity data that matches the environment, or allows me to add noise to model it, and also has diverse enough environment. So I can be in a suburban environment and see a traffic light, or I can be in like a rural environment and see like a tractor or something, you know. Yeah, does that kind of answer your question? Yeah. Okay. So these are like trying to use machine learning approaches to figure out what it is that went wrong, figure out like what needs to be improved, what is that delta, and try to relearn it. So NVIDIA is a great resource for a lot of simulators. You might have heard of like Isaac Lab, Isaac Sim. Those are pretty good, very scalable environments. But I'm fairly certain that at least the versions that I've used don't have like battery modeling in that example. And they don't have many like diverse environments. You'd have to like build your own environment and import it, versus something like the Unity simulators, since it's like a game engine, it does a much better job of the physics simulation, about battery simulation, things like that. So if that's a priority, there are certain people in my lab who use that. I think this one is interesting, where here what we're learning is like system ID of the environment. So we talked about system ID of the robot and what is like wrong with it, right? Like what is wrong with my 10-year-old robot versus the robot that just came out of the factory, versus what is different in my environment from what I'm used to, and how do I need to change my execution accordingly. So that's what this last one is. That's just to identify the difference between some of these.
This one is similar to our idea of using some Oracle budget to adapt to current task, right?
Which one? The last one?
Yeah, you could like, your robot could have sort of self-configuration that you can like start it, and it takes a couple of minutes to
Figure it out.
understand what's going on.
Yeah. So this is, yeah, exactly. Like it's basically like localizing itself or orienting itself in the new environment. So like usually for map building, they'll take some time to just explore around the region, work on a small map, relocalize themselves in the larger environment, and then you can start your execution. So it's exactly the same idea of what it's doing. All right. So for people working with VLMs, these are issues either that I have run into, or there are people in my lab thinking about problems like this. So this problem of, we talked about slippery surface, right? That's exactly like what I'm trying to get at here. So VLMs can understand that, you know, this is a mug, right, let's say. But if there was oil on the mug or if there was water on the mug, and it tried to pick it up, it could just slip from the grasp. So we can assess it, and then we have a sense of the physical characteristics. We have a sense of like, this is what is different from what it should be, and this is probably why it's there. So let's be extra careful. But this notion of extra careful, like, isn't necessarily built in. Like, people are working on trying to get VLMs to have this better like physical grounding. But it's a lot harder to use just vision to try to figure out these characteristics. So a few of my like peers in my lab group were working on this problem, or they tried to work on this problem where what they were trying to do was they like had various wooden blocks of different lengths, different widths, and different weights, right? Like oak versus like birch versus like balsa is going to be very different weights, right? So depending on the porosity. So even for us looking at it, we don't have a sense of, is that easy to lift up or not sometimes, right? You can use your intuition based on size, but it's much harder to estimate your density and therefore the weight. And even VLMs, like, so they started off with just the problem of, can you pick up and the reason I'm talking about this is because they just try to do direct robot execution. So we had like a gripper on the table and then different objects, and we try to have the VLM directly use an output to figure it out. And even with size, like up to a certain length, like I think this big, it was like, yeah, you could pick that up, no problem. Which is probably true, but like it wasn't very good at dealing with, definitely could not predict density. But even with the sizing or like width, your perspective affects maybe how large you think the object is. Similarly, like this table is probably not something I can lift with one hand, right? It's a little too wide, and maybe it's not too heavy, but it's definitely too like bulky for me. So the sense of like, what is the physical embodiment that's trying to execute the task? The VLM might say, this is a really hard thing for you to pick up. But if it's a crane, this is super easy for a crane to pick up, right? And so this understanding of like, this is how big this object is, or this is how wet the object is, are not abilities that a VLM has. So to your point, yes, you can maybe use vision to figure certain things out, but there definitely is a limit to how much information you can extract from it and then use it to inform the policy. And if you think about it, that's so many different variables to consider, right? Is it wet? Is it not? Is it tall? Is it not? Is it like, how heavy is it? Like that itself has a range of values that it could be. So even material, right? Things that look like metal could be made of plastic. So you go in like thinking you need to grip it really heavily and then it just like flies away. Yeah.
Yeah, one more question.
Yeah.
About environment, but about the physical robot itself.
Sure.
Is there any kind of expectation in the simulation modeling, like any expectation of robots are being co-programmed or plug-in made, and how is that treated in the simulation environment?
Like you're saying the robot material itself.
Yeah, so the interaction with the environment will change.
So typically, at least what we try to do is if I'm working with a cheetah, like a spot, I would want to be using a spot in my simulation. So I'd want to drop spot in there. So Boston Dynamics, for example, has the spot API and has like models available, like SDF files and models available that allow you to take this robot, all its joints, all its body parts, and drop it into any new signal. So I am then making the assumption that I haven't gone and modified my robot, right? So if you're working with pretty like commercial robots, except like very commercial robots, so Unitree robots, Boston Dynamics robots, things like that, they're very well like modeled in simulation for the most part. Like you can basically take the model file and drop it into whatever simulator you're working with. And then like if you've gone and modified it, then you would have to go in and like change the SDF file and maybe add a characteristic on top. So typically with these SDF files, I think there are versions where maybe you can't specify a weight, but you can specify materials for certain things. and maybe their densities or something. Like there's a place where you can specify information about the obstacles and the objects. So that's a place you could go in and change. But ideally, like if you're saying, I'm training my robot in sim and then I'm executing it, if you change platforms, you will definitely run into issues, right? If you try to keep those platforms consistent, then it's less likely that you're going to have those kinds of issues. So I don't know if you guys have tested or like flown any drones to collect data or like where real robots might fit in your current pipelines. But for example, DJI drones, or I can't really think of some of the other ones that are in sim, but like many of these quadcopters are very similar. You can drop them in and their characteristics are going to be well modeled. So like part of the assumption is that you are training with the same thing that you're testing with, knowing that they're going to be like, for example, our robot in sim did not have a laptop on top. Our real robot did have a laptop on top, but when we like placed the laptop on, we tried to make sure it was over the center of mass so that it wouldn't affect balance issues across the robot. The other thing to note is, especially robots like Unitary robots and Boston Dynamics robots, a big part of their like what makes them so usable in the real world is that they have systems built in which allow for correction, right? So your policy can say something, but it will take that and it will make the most of it. Meaning like if it's going to crash you into the wall, their own safety systems will kick in. Or like one side feels weaker, like the policy is, telling both sides to put out, say, 10 units of whatever forward or 10 units from the motors, but only 8 is being produced, right? So maybe one of the motors is a little weaker. Then either the other one will also reduce to 8 or both will, or this one will try to go to 12, so it comes back to 10. Yeah. So there are, depending on the robot you use, there are either fail-safes available during real-time execution for some of these slight issues. But for the most part, it's good practice to just try to model your robots as well as you can in simulation. Whether you build that up yourself or you use a commercial robot and therefore have a commercial simulation of it. Yeah.
Back to your previous point on communications with vision language models, and then of course
Sorry, which one? This one?
yeah, like about the limitations in each approach,
Yeah.
whether it's VLM or simulation. Do you think moving forward, even if we limitations, do you think companies will still employ more combined approach when they, even if they focus on simulation, they still employ imitation learning? Or do you think one or maybe all of them will improve so that for certain tasks, one approach will be enough?
That's a good question. I think like even when you think of imitation versus reinforcement learning, for like different approaches are developed because there's some boundary or some border where one is better than the other, right? So for example, for small examples, imitation learning is a lot better because it's very expensive to like spin out a whole reinforcement learning model. It might learn things which you don't want it to learn. And then as you start increasing in size, RL models are better than IL. So that's one, that's just a case in point. But in the same way, like VLMs might become great, but there's always going to be certain situations where they might fail or, whatever, something happens. And so for sure, for like commercial deployments, they're not going to rely on just one model, right? Like they have a layer of models and then maybe like fuse the outputs together and make some sort of sense of it. I could see a world where like VLMs get better at like they have a better sense of physical embodiment and what it means to like execute a task, like for a robot to execute a task, right? VLMs are great at doing all the visual things because there's so much data for that, but there's no like robot action data that is fed into those models. So if there's a robotic specific VLM that gets developed, then maybe it'll, solve 95% of the tasks. For that 5%, I don't know what it would, you'd have to look at the cases where it fails and see what fixes those things. But I definitely don't believe that, in research, I think generally we're okay with having a solution that works 95% of the time. And then you just say like, the rest is future work, or the rest is like something we'll look at later, or something that someone else will engineer a solution for. But if you have like a car driving out on the road, or you have a robot that's going to do search and rescue, or like the police are putting some robot out to find someone, right? Like you care about that level of accuracy, and you care about like really good execution. So all that's to say that I do think VLMs are going to improve. I do think that they're going to like take over a lot of these like small engineering solutions we've tried to hack together to solve the problems, but I don't think they're going to solve everything. So we still need some other supplemental models to help. Does that answer your question? So here is a very obvious example of like of latency, right? So if you're trying to query a VLM at every second, unless it's a very small model, you have a small model, it may not do as well, but if you have a small model, sure, you might be able to do it very frequently. But for the type of tasks that people who are using VLMs, would want to execute, you have a pretty long execution time, and you need to be, continuously giving robots commands to do. So this solution of using a VLM as like a high level occasional query, and then using something else trained as a low level executor is the like general approach that people are taking. And that's the approach that I'm taking, for example, right? So in this case, whether it's a VLM or so the LiDAR gets used at every step, but I think I mentioned this during my earlier presentations, but when I start using VLMs, I'm just planning to use it every 5 or 10 seconds, or at an important junction, for example, like when a new cluster is identified. Yeah, so I think generally this is self-explanatory. If you've worked with VLMs, you kind of can see their limitations pretty easily. And it's really interesting to me that there are so many roboticists who are kind of going down this like VLM only path, or like VLMs are like going to take over the world type path. And I do think, again, like I said in like the answer to the previous question, I do think like they're pretty good, but they're not great at everything, and you can't rely on them completely. So I am curious to see how well they improve, especially at like spatial tasks and these physical characteristic tasks. Okay, there's a lot of text here, but it's important to distinguish like what types of sim2Real problems are quote unquote solved for the most part, and then what have gaps that need to be solved. So you have line locomotion with quadrupeds or bipeds. So again, when we talk about Unitary and Boston Dynamics, that falls under this umbrella. A lot of their work is basically this, where you have a framework where you learn what it is in the perfect environment. So that's what the teacher is. And the student gets information from the sensors and then tries to infer the properties and then execute the task accordingly. And that's what allows it to, in training, it hasn't, like maybe the ice dynamics are not well modeled in simulation, but in the real world, like it might slip and then it'll figure out why it slipped and then recover. So a lot of times when you see those videos of people like kicking the robots and then it readjusts, right? It'll like fall. It'll like, like stumble and then it'll recover itself. And the fact that it can do that recovery is like, no one can predict exactly how the robot's going to be kicked by a human, right? You can't simulate all those types of things, but it is learned that like when my joints maybe, or like when I get the sensor information from my joints or from my RMU, then I need to do this type of corrective action. So that's what this RMA or rapid motor adaptation is. For the middle one, it, let's see, high level is how do you, when dealing with vision and simulation versus real world, how do you work around that? So people are trying to train in featureless environments so that you learn the collision avoidance, you learn all these characteristics, and then
what do you mean by featureless?
So instead of a tree in the environment, he represented like a cylinder. So that's what this is. So treats the real world tree and the sim world cylinder is the same, using like dino features or whatever it is that you're encountering in the real world. And there, the idea is like if the abstract features model the things that you're seeing in your environment, you can learn how to navigate around them. And then when you get a tree or you get a pole or you get a building, it doesn't really matter. You've learned how to navigate around that thing. And it doesn't matter that it's a tree. Like trees themselves can be, they can come in different shapes and sizes and look like different colors and be interpreted differently. So as long as you're processing that feature, that latent feature as the same thing, it'll handle that in the environment in the same way. So the point of this is like when you're dealing with drone racing, these are situations where your environment, your real world environment, is mapped into the simulation. So if you had like loops or like hoops, and then you had like a pole, and then you had a net, you could simulate those you could like put those into the simulator. But what they're doing is instead of representing the pole as a pole, it's a cylinder. I guess pole is a bad example. Instead of representing a traffic light as a traffic light, you represent it as a pole in the environment. And then that way you're also removing the need for the simulator to handle all those graphics and stuff, right? Like, so you can run it faster and you can run more iterations of the same. And then pick and place tasks are like quite robust when you think about manipulation problems, assuming you have like a rigid body. So this would count as a rigid body, but my hair would not be considered a rigid body, right? So pick and place of these types of tasks are pretty good, and they have done so with domain randomization. So we talked about like changing the simulator, changing the things in the environment, but specifically massive domain randomization. So manipulation tasks are much easier to like spawn up than trajectories, like long trajectories. So you can run like in Isaac Sim or Isaac Lab, for example, you can run 1,000 tabletop manipulators at the same time and train it. So each of them could have a different variable that's changed. And then you're generating massive amounts of data. Your policy is learning a lot of things. And then together it becomes like immune to whatever noise you could encounter, whether that's visual noise or some of the physics that are modeled and things that you could encounter in it. So things that need some solving are contact rich or deformable objects. So like I said, rigid body is good, soft body isn't good. So a lot of people are working on soft manipulation, right? So fragile objects, for example, like if you had to hold a baby, you're not going to grip onto it the way you would grip onto a chair, for example, right? And we know that, but a robot doesn't necessarily know that. So how do you deal with that? And that's really important because there's an example of like peeling a grape. When you peel a grape, like it takes a bit of effort to like break the surface and whatever. And modeling those kinds of things are quite hard. Like if you've seen, so people have like tried to simulate something like that, it'll just squish the grape because it just applies too much force. It doesn't have this concept of peeling. So things like that are, again, quite expensive to simulate in modern simulators. So it's there still is an open question of, do you want to improve the simulators? Do you want to generate multiple examples from real robots? Like what is the best approach for a task like that? This one is, I don't know that there's like a solvable problem to this unless like, this is basically saying your hardware has to be perfect all the time. And that's a very hard ask. Like everything will have some type of defect in it. So this is just a constant issue. It's more of something to be cognizant about when you actually execute tasks. And then the VLM problems that we talked about, which I think are on the mend. Like I think there is progress towards better VLMs and how people are thinking about using them. And that'll probably remove many of the sim2Real gaps that are still involved when you use visual tasks or when you're relying on vision or when you're trying to use VLMs for visual tasks. So these are, I guess we talked about this, kind of. We didn't talk about it. I guess I talked about it, but I'm curious to hear if any of you have thoughts on any of these questions, either based on your experience or things that are interesting to you or things you've read about. The first one being like, we maybe are making certain assumptions about what VLMs have learned and what they know about execution in the real world. In some ways, these kind of go together. So any thoughts on that? And then this one, I kind of put this one down for the drone group or like the VLM group where if you're learning how to navigate or you're outputting commands based on spatial information, when you actually go to execute it, how do you think you're gonna have to deal with like resolution of your images, or like it's trained a certain way and then during execution it receives different type of data or it needs a higher level of granularity. So it's open. I mean, anyone who has thoughts is welcome to share their thoughts. Actually, before that, can I get a show of hands? How many of you have worked with real robots with your research? Just me? Yeah, physically. No? Okay, all right. Anyone have interest in that kind of stuff? Okay, all right.
Look, I think one general assumption that I think is reasonable to take now is that the hardware perfection is not going to and in fact it's going to be worse because a lot of the robots will go to mass production. Like if Boston Dynamics produces 10 robots or 100 robots a year, you can't assume that they are good enough. But if it's going to be like every household has a couple of robots and stuff, you should never assume that any of this should be perfect. So it's good news for us kind of to work on the things, first of all. The other thing that I want to say is that I believe that the VLM hub has an interesting advantage that I don't know how to formulate. Can you go back to the video when you were pushing the robot to go forward and so look, it's going to become a little bit more philosophical, but when we are talking about robotics and abstractions of the world, sometimes we talk about concepts that we as humans have developed to help our research or our work, but they are not directly tied to the goal that we're trying to solve. So this can become a feature of deep learning. So in NLP, I mean, it's very famous, right? So there was this concept of semantic parsing of sentences that computational linguists thought that this is an important step, that if you want to understand the text, you need to understand the semantics, you need to understand which word is connected to which word, right? And this will be useful, for example, in translation. But then eventually translation was solved without this, right? So it's solved with an end-to-end kind of thing because you actually cared about the final result. You didn't care about these intermediate steps. These intermediate steps were invented by researchers to make their work easier, manageable. But this, in some sense, these were like fake targets that decades of research was chasing, right? And then it turned out that you don't need that. So there was this lecture by Ross, is the guy behind a lot of object detectors, like Foster, CNN, and all these famous papers. I think it was in 2024 CVPR. He had this lecture where he said that he believes that object detection, when you take a picture and look for a bounding box, this is also a fake target. Like we have invented this task to advance computer vision, but actually it's not clear why it is a goal, right? So if you think about like what a robot wants to do, it's not about bounding boxing an object, right? It's about, I don't know, making a coffee,
Sure.
which might involve some object detection, but it's like an intermediate whatever that the robot might want to do somewhere. So I'm trying to argue that this task of getting straight
Mhm.
is also kind of fake target, because whatever, actually what you want is to, for example, reach that particular
Sure. Like
metal
the
or whatever,
pole,
right?
yeah.
So if you think that way, if your goal is to go to that object
Mhm.
or that coordinate, it's not about driving straight,
Yeah.
right? So, and if you're due to hardware limitations, or I don't know, there is a strong wind, there is something else that is
Mhm.
not letting you to drive straight. If your goal is to reach that thing, then your actions would be not to just push forward, but like every, I don't know, 20 seconds,
Yeah.
calibrate what you're trying to do.
Yeah.
Because your goal is to reach that point. Your goal is not to drive straight.
Like you're
right?
saying, if you're using a VLM and you reach this point,
Uh-huh.
you're pointed at the wrong pole, so you know that you have to recorrect.
Yeah, so if
Right,
you if you tell your VLM that, I don't know, I need to go to this location.
Yeah.
And at this location, it decides that, okay, I should probably move straight. And then it drives straight, and then for some reason it doesn't go straight, it goes to the right. Then the VLM can remember what was my goal. My goal was to go to here, so now I need to turn left a little bit, for example,
Okay.
right? So if you're trying to think with this kind of mindset, these problems seem to be not very critical, that
Oh, yeah, for
you
sure.
have this gap. If you have the ability to correct yourself, if you have the ability to rethink your action on the fly, it's actually very similar to what you said about dogs when some people keep
Mhm.
the robot, right? So
Yeah.
if you have this ability to recover and get back to the actions that drive to your goal.
Yeah.
These gaps are not very dangerous, but maybe not all the gaps.
No,
Maybe
yeah.
there are things that you still need to be careful. For example, the one that you mentioned is this latency problem. So probably you need to be aware that once you take the picture of this state
Mhm.
and process it through your VLM, the reality has moved forward. So I think that is something that we should probably start integrating into the pipelines that work with VLMs. For example, when you do, I don't know, OpenFly or whatever, when you do Unreal Engine, can we simulate that, for example, if I'm a drone and my VLM predicted this,
Yeah, for
and then at the next iteration, when I'm getting the new signal, my simulator should continue to run with kind of real speed before my action comes. Right? Because right now, as you said, simulator freezes before the.
I think it still will execute whatever the previous policy was. So like, if you say forward, but now you need to go left, but the next policy update is only 5 seconds later, you'll go forward for 5 seconds.
Exactly.
And then you'll update, but everything will have that 5-second lag, kind of, right?
Uh-huh.
Like you might have only had to go forward 1 second, and then you've gone forward 5.
I think this is something that you have to integrate into the simulator, into your simulator, into the environment where you're learning or you're playing. That this feature of it, that the moment when it sends the capture to the VLM and receives the signal, the simulation doesn't stop. It should continue with its own physics, whatever it is, like with its inertia, with whatever, it should continue to fly or move, and only then get the signal. So if this is simulated, then the model might learn about this potential gap, even this lag, right? Because it might see that, especially in the RLH.
So I think the lag that I'm referring to here is like step to step, like by default, the sims will keep running, like they won't ever stop, I think, unless there's a, like, yeah, I think by default, they will just continue. But the issue I'm talking about is like when certain parts of your code execute really slowly, like in theory, if my VLM went really quickly, I would love to query it every, like twice a second.
Let's imagine it's not. So it's slow, and
Mhm.
this is the simulation time,
Yeah,
and this is, there is no pause, okay? So
it just keeps going, yeah.
it keeps going. So then, for example, at this time point, like you said, like every 5 seconds or whatever, I want to ask for VLM
To give me
to
a
do
look.
something,
Yeah.
right? So at this point, what I should do, I should take a picture capture from the simulator. Right. So it gives a picture. This goes to VLM. It takes time before VLM actually produces an action. And then this action is executed here. So the simulation didn't stop.
Correct.
It was so like technically it should be on its own hardware thread, whatever. Like
Yes.
it could be on a different machine that is doesn't interfere with the other thing. And then if the entire training pipeline is designed this way, then even like we're talking about GRPO or things like that, VLM might have the signal that whatever I'm going to produce is usually based on an old state of the world, and I should kind of anticipate what will happen in the next, I don't know, 1 second or 2 seconds to make the decision that will be useful in the future, in some sense, right? So I think this is something that, for example, in our research is missing. Our simulator is so dumb that it doesn't care, right? It doesn't even have the physical object there. Like we just, I usually say that we are a flying camera. We're not a drone. It's like
our drone waits until the response comes and we
yes.
Okay, so it's like a very step by step, like it executes it and then it goes to the next step.
Yeah. So like the better version would be to have a real simulator running, like the tutorial for that should be run the simulator on a different separate machine.
Yeah. What are you using right now?
Unreal.
Okay. And like I'm assuming you've like imported your own world and your stuff like that.
These papers
Yeah.
give their worlds, their environment.
Okay, so you just take those.
Yeah, we just take them. We don't even think about it.
Okay.
But then probably we should add the training, and then the output of this VLM should be relatively high level, just like this. It should be remote control, whatever. It shouldn't be like this motor speed, whatever. Okay, so it should be very high level. There will be some controller here that interprets this high level action and translates it into low level control. And then this will be executed by the simulator. And then maybe next time step when the VLM. So the physical concept of time should be included in our work that we don't have it now.
Okay.
I think that's one important lesson here. On the other hand, I think some of those real world problems. Awesome.
I was curious, what the relation was your solution and the program that you have?
Yeah, so if we're talking about this particular one, I think it should still be go to that particular object.
Yeah.
And then we shouldn't care if the simulation or reality are diverging from going straight. Because at each step, we're going to repeat the instruction and take action based on the current situation.
So you're saying like, if we were to solve this problem with the VLM, we don't have
Yes.
to care about
Yep.
going straight as a problem. But in the situation where we don't use a VLM in the pipeline, then this becomes an issue.
Yes.
Or in the situation where the VLM isn't able to identify that, I mean, I can't think of something off the top of my head, but in a situation where the VLM fails to identify a corrective action, then we'll still encounter the same issue.
Yeah, but
right?
my I think I want to say that this video is designed to be an illustration.
Yes,
Even
exactly.
a simple thing like going
Correct.
straight is a problem. And I'm trying to say that going straight is kind of a fake target. So this is a problem as long as you just want to go straight. But if you're going to specific objects, like I'm going to this flag or whatever, then your system can be designed in a way that this type of inaccuracies or shifts in the world that was not expected in the simulator are solvable, they are okay.
Yeah.
And if you want to make sure that your model is robust to those things, yeah, you should try to have this type of noises in your simulator.
Yeah.
And I think you had a good point on that, like how can you add weird types of noise and interruptions and in case of drones, we have this discussion that at some point this simulator in Unreal or whatever, they should have a concept of weather, of wind,
Yeah.
of something, right? That is just added there. I think many current simulators have it.
Yeah, for sure.
It's just
Is there a
in
reason that
this
you
line of
chose?
research, they don't use them. I mean, I haven't seen a.
Okay, is there a reason that you chose the Unreal Engine simulator?
We took it from existing papers. We didn't develop the bench.
Yeah, okay, as in you just chose it because people have
That's
done.
the only that exists.
Yeah, because to the point that there are multiple simulators that do it already, especially if you're not and like putting the embodiment of the drone in, if you don't care about that. There are a lot of simulators which will include those types of environments that you care about, either different environments or you can tweak the weather. And like, for example, Carla, if you took out, so if you didn't care about the physics really, like if you didn't care the physics of the drone, you can just turn off physics in the environment and then the car can fly. They can just ignore that it's a car, just pretend it's a drone. And they have like 12 different environments. They have like different, you can toggle the weather, you can have it rain, you can have, whatever it might be. And they're pretty good like environments as well. So I think like, especially if it's early stage, of your interaction with the simulator and you're getting frustrated, I think it's more important to find a simulator that you can like tweak a few things and it gets you to where you want to be than trying to like build it up from the ground. Like Unreal and Unity are very hard to work with if you don't have a lot of experience working with simulators or game engines. And that's what I ran into. So I like was working with the Unity sim for a long time, and then someone in my lab was doing the spot in an Unreal Engine sim, but then the problem was it didn't have the diversity of environments I cared for. So that wasn't useful for me. And so then that's why I switched to Carla. And I'm not using, I mean, again, I used the car, I like changed the car behaviors to match my needs. And I think a drone is even easier to just model, especially if you don't care about the physical object and simulating that.
I think we should care,
I agree that you should care, but for now, if you don't.
Another difference in AI research compared to basically every other thing that I have seen is that AI research is very much benchmark driven.
Very much what, sorry.
Benchmark driven. So,
Yeah.
This entire the reason that we are like easily talking about Dyno V2 and it helps in lots of things is just because in 2011 some people at Stanford have created ImageNet, which became the standard benchmark for computer vision, and it kind of caused this whole explosion of deep learning models, right?
Yeah.
And That's how people discovered and invented vision transformers. That's how it became Dino, whatever. So, and this is both good and bad. So it's good because it allows different researchers to compare their results with each other, right? For example, if you are testing your system of robot in MIT hallways, it's hard for another team in, I don't know, Texas.
Yeah.
To compare their robot or their solution with yours, right?
Correct.
Because they have different hallways. In AI, this part is kind of solved because
Sure.
everyone is using the same set of benchmarks. But the other problem is that if the benchmark is not good, like a lot of brain power of AI researchers is wasted on solving the wrong problem, which happened a lot. Like, for example, in chemistry, there are molecular property prediction benchmarks, which are known to be like very faulty.
Okay.
Like a good result of those benchmarks is not anything, but there are like maybe 500 papers.
That's so unique.
And yeah, there are people like if I see this benchmark name in a paper, I don't read it because it's not. Okay, but it still happens because
Sure.
AI people are not really aware of these issues. So I'm afraid that something similar is happening here. So the benchmarks that we are working on are not that good, are not that representative of the real problems. That's why a lot of the things that we are developing might be a little bit off, right? So as a researcher, for us, it's an important problem to understand what